Good morning, class. How are you?
Good. How are you?
I'm good. Are you sleepy?
Every day.
Every day, all the time? Okay, good. We'll do some mathematical problem.
Yeah.
So you'll be out. Okay, so all of you should have one class lecture, lecture 7, and one bubble bottle or something. I don't know the exact name of that. Okay. So we started the class example 4, I think in our last class very briefly, right? We will complete that. And one thing, today we will be done with hopefully we'll be done with our fluid properties, and you will have your test 1 next Wednesday, okay? The syllabus for test 1 will be only the fluid properties, and on Monday we will have a review class. We will just go through what we did very briefly, and if you have any questions, we will discuss those on Monday. Okay? So after today, once we are done with class example 4, you will be ready for your homework 2, because there will be one question about your lab experiment. You did that in last Monday. You took some measurement, right? So that will be a part of your homework 2, and there will be a question about viscosity calculation. So once we are done with class example 4, it should be fine. Let's start working on class example 4, okay? So I think you read the class example 4 in our last class. Mainly the question was, there is a setup here, and these are fixed surface, right? And in between these two surfaces, there is a liquid, but in between liquid, there is another plate, and the top part is called A, and maybe the bottom part is called B, and they are asking you to find what will be the force you're pulling this plate so that the velocity of that plate will be 6 millimeters per second, right? That is the question. Now, we will solve that. Now, from this question, you can see for this plate here, obviously, on top of that plate and the bottom of that plate, there is a fluid, right? So what we will do, we will calculate the top part and the bottom part separately to find the force, and then we will add those together to get the total force, okay? And here, that was the kind of schematic diagram for this problem. Since this is fixed, what will be the velocity on top? Here, the velocity will be 0. And what is the velocity here? Do we know the velocity on top of this plate? Good, 6 millimeters per second. Again, the velocity is 0 here, and velocity here is 6 millimeters per second, right? And let's write down what are the given values for this problem, and then we will find out how we can find the force P. Now, one thing is confusing in this question. We usually use P for pressure, not for force, but here they just use P for force, so you keep that in mind that for this problem, P equals to force, okay? So let's write down all the given values. What are the given values for this problem? The first thing is what? The kinematic viscosity, right? So I will write down that. So this kinematic viscosity, we represent that by mu, which is pretty similar to V, but it's not V. It's called mu, and the value is 4.545 10 to the power 5 meters square per second. If you look at the unit, it says that meter square per second. That means per second that area this fluid can cover. So that's basically that is kind of an indicator of viscosity. Obviously, if it's less viscous, it will cover more area, right? Within 1 second. And if it is more viscous, obviously it will cover less area. That's why it's meter square per second. What else we know? What else is given from this part? Read the question and tell me. Density, yes. Okay. So density is 880 kg per meter cube, right? Okay. Do we know anything else? We know the velocity, right? There is a slight difference in speed and velocity. Speed is like directionless. And in any direction, if you go with some uh, length over time, that will be the speed. But for velocity, you will have some direction. So 6 millimeter per second. Those are the given values. And we need to find what? Force required, right? This one. And do we know the dimension of each layer? What is the dimension here?
6.
6 millimeter?
4.
And 4. Okay. And what is the dimension here? What is the unit?
Meter.
Okay. And what is the dimension here? What is the length of the plate? Point 2. Okay. So these are all the given values, and we need to find the force required. That's what we need to calculate. So once you are done with this slide, we can go to the next one. Everyone is done with given values and what we need to find. Okay, good. Now, as I said, since this piece, it will be affected by the top layer and the bottom layer of fluid, we will calculate those layers separately. At first, I will work with the top layer, okay? And I will draw the picture again because I will need some value here. That is P. That is the velocity profile here. U equals to 0, U equals to 6 millimeter per second. And if I start a scale, Y equals to 0, what will be Y here? What is the value of Y? What is the total depth of this layer?
6 millimeter.
So it will be 6 millimeter, right? Okay. Now, since it's viscosity and we just learned about Newton's law of viscosity, so we can start working on that equation. So Newton's law of viscosity was what? Tau equals to this one, right? Now in this equation, I'm not seeing any term. I'm not seeing any force term here. I'm just seeing stress and something else. Is there any way I can convert something into force from this equation? I'm not seeing any force term. I'm seeing stress, viscosity, velocity, and some y. Is there any way I can convert something to get force term here? Like how can I use this equation to calculate force? I'm not seeing any force term. Say it loudly, I can't hear. Great. Yes. So stress equals to actually force over area, right? So that's how I can convert that. So it should be force over area mu du over dy, right? Now I can say force equals to area. Now, if you look at the given values, I don't know the mu value. I know something else, which is mu. So I need to connect the mu and mu also. And the connection is, we covered in our last class, mu equals to mu over rho. So that's what I will just write here. Du over dy. Okay. Since this time we are only working with the top layer, I will write down force equals to P top, A top. What is the velocity? What is the value for mu? Can you tell me, fourth one? What is the value for mu? 5, 10 to the power 5, right? Meter square second. What is the value for density? 880 kg per meter cube. Now, du, I need to go to this picture. Du means the difference in velocity. So, here, the difference in velocity is what? 0 to 6 millimeter per second, right? From this picture, from this point to this point. And what is dy? 0 to 6. Are you seeing how I got that from this velocity profile? So in between this portion, it's 0 to 6. That is the velocity difference. And what is the length difference? 0 to 6, right? Everyone's good up to this point? I will write down that 0 to 6 millimeter per second. And here 0 to 6 millimeter. Okay, now we know millimeter is not the standard unit of the length, right? So we should convert the unit to meter, but on top and bottom, we are having the same unit, millimeter, millimeter. Eventually, they will get cancelled. So if you want, you can convert the unit. If you want, you can keep that as it is. It will not change the result, but it's always good practice to convert. So it's on you. If you want to convert, do that. If you don't need, if you don't want to convert, you can keep that as it is. Okay? Okay. So now tell me, what will be the area? I'm going back to the previous slide just to show you. Tell me which area is affected if you pull that peak, like or that plate. What is the area which is getting in charge? Like this one, right? Like it should be like if I draw here, that is the area which is getting affected, right? So what is the area? What is the magnitude of that area? What will be the area? Give me that. That is the plate. You know this distance. You know this distance. What will be the area? Say it again. 300. So you're saying like it's 0.15 multiplied with 0.2. So yes, 0.15 multiplied with 0.2, right? Like this area and this area, this one. That's what you're saying. Okay. So everyone else, you need to participate in the class also, okay? Otherwise, I will just stop here and I will just stand here. I will not do anything else. And at the end of the class, I will just say, okay, I covered everything. This will be on your test. So you need to participate. Okay, now it's 4.545, 10 to the power 5 meters square per second, 880 kg per meter cube. And here it's 6 millimeter per second and 6 millimeter. Okay, so what will be the answer here? While you are working with the number, I will write down the unit here so that we can see what will be the final unit. Okay. So for the area, it's meter square. Everyone, please calculate. I will ask the answer. Meter square per second, kg per meter cube, millimeter per second, and millimeter. So that is the unit here. You just give me the final number. What will be the final number? 0.0012. Okay, anyone else got something similar to that? 0.0012. Everyone? Okay, then what is the correct answer? I got the same number. 1, 2. Okay, now since we are working with the force in SI unit, what will be the unit here? It should be Newton. Now, it should be Newtons. Now we need to work out, we just need to check whether our unit calculation is correct or not. So I just wrote down all the units here on top of that line. Let's cancel some unit and let's see if we can simplify that. So I can cancel millimeter, right? I can cancel 1m, and with 1m that should be just m. So finally we have what? Kg meter per second square, right? So kg is the unit of what? Mass, and meter per second square is the unit of what? Acceleration, right? So basically mass times acceleration, or ma, which is what? Force, right? Force equals to ma. So that's why we can use n, and our unit calculation is correct. Now that is just the top part. We need to calculate the bottom part as well, right? So right now you will do the bottom part. You have 2 minutes. Do the calculation. I will walk around the class. If you need any help, any confusion, I can help. Okay. What will be the only change for the bottom part? What will be the only change? That's the thickness of the lower unit part, right?
Oh,
Because everything else is same here. The area is same, the velocity performance is same. Only change is the thickness of the fluid, right?
so we just do that.
Yeah. So work on that. Everything is on the board. The only difference will be, instead of 6 millimeter, we need to use the thickness of the lower part of the fluid. Do that. And once you are done, tell me that. Then I will work on the board. 0.0018. All of you are done with this slide, everyone. So one of your friends got 0.0018. Once you are done, just tell me what number you got.
Zero
0.0018. You also got the same number. Okay, I will wait for you other people here. 0.0018.
Yes.
Okay. So it seems the correct answer, all of you got the same number. Okay, and if I start the scale, y equals to 0, y equals to, what will be the y on top of the plate here? This time it's we are working with the bottom layer. So what will be the y here? Y will be 4 meters. So du will be still same, 0 to 6 millimeter per second, and dy will be 0 to 4 millimeter, right? Okay, I will write down all the numbers very quickly because everything else is same. 4 point. You are correct. Yes, that should be 0.2. 10 to the power 5, 880. Du will be 0 to 6. Du will be 0 to 4. And if you do the calculation properly, yes, your answer is correct. It should be 0.018. And the unit will be what? Meters. Now we know the force for the top part. Now we know the force from the bottom part. So the total force will be what? P top plus P bottom 0.012 0.018 Newton. So final answer will be what? 0.001. Yes. So that is the amount is needed by the plate. If you pull that plate by that amount of force, the velocity at the plate will be 6 millimeters per second based on this type of fluid. If the fluid is different, obviously the viscosity and the resistance will be different and the answer will be different also, right? Okay, now you are ready for your homework 2, which will be available today. There will be one problem about viscosity, pretty much similar to this one. And there will be another one which will be a little bit different, but the steps are same. Okay, so you can open your homework 2 once I upload that, and you can start working on that. Are we good with viscosity? Any question? Anything? Everyone's good? Okay. If everyone's good, we can start the last fluid property we will discuss, which is the surface tension. Okay. So from the name surface tension, you know it's related to surface and it's related to some tension force. So what is tension force? Not the mental tension, just the tension from concrete or structural theory. Compress is when you apply some force, right? And the tension is when you pull something, right? On any direction. So here we will see based on different type of force, sometimes we can have some pulling type of force in the surface also. Now, before that, we need to know two type of forces. One is the cohesive or cohesion, and the another one is the adhesive or adhesion. I think you know the word adhesive, right? Sometimes you say, okay, the duct tape is adhesive. Why is that? Because it will stick to something else, right? So the cohesion force is the force between same types of molecules. Okay. So in your copy, there are some blank spaces. You may want to write down the word here. So when the bonding between similar type of molecules is actually the cohesion forces or cohesive force, that means H2O, H2O, when there is a bonding between same type of particles, that is actually the cohesive. Like they are so content with each other, they don't need to make any bond with others. The adhesion force is when there is a bonding between different type of particles or substance. Okay, here. So a good example can be H2O and the air molecules bonding, or H2O glass container molecules bonding. Like wherever there is a bonding between two different type of particles, that will be the adhesion. And whenever there is a bonding between the same type of particles, that should be the cohesive force or force. Okay. And based on these two force, like based on the magnitude of these two types of different force, we can explain the surface tension. That's what we will do. From back, can you see my handwriting? Okay, and you can hear me clearly? Okay, so let's discuss the surface tension with these examples. So this is a glass container filled with water, or any container filled with water, and we have three different type of sceneries here. So I will just number that. So this one is number 1. Okay, this one is number 2, and these things, that is number 3. Now for number 1, what type of force is acting on the molecules here? Cohesive or adhesive? It's the same type of particle, so it's a cohesive or adhesive force here. Point 1. Big cohesive, yes. And what about number 2? Cohesive or adhesive? This bonding between the water particles, same type of particles. So again, it's cohesive, right? Now, for 1 and 2, you are seeing the like each particle is connected with other particles in all the other directions. So there is no net force because that is neutralized by the particle force from the other particles and everything. Now, for point number 3, what are the different type of forces we have here? We have cohesive, right? Bonding between H2O, H2O particles. And do we have the adhesive force here also? In between H2O air, right? And obviously that adhesive force is less than the cohesive force they are experiencing. So there will be a net force in which direction? In upward direction or the downward direction? In which direction there will be a net force? There will be a net force in downward direction. We can see that from the picture here, right? And because of this force, it's like this downward pulling direction force that will create the tension on the surface. And that is actually the surface tension. Okay. And because of surface tension, maybe you saw some videos like where insect can walk on the water. That is because of surface tension. For surface tension, you will see the raindrop is circular because of the insect surface tension. Okay. So that is basically the surface tension. That is the concept. And if I want to define the surface tension, basically it will be the work or energy required to remove the surface layer of molecules. It's like if you want to remove the surface layer molecules, the work you need to do, that is actually the magnitude of the surface tension. There is another definition also. I will discuss that in a bit. So usually we express the surface tension by sigma, okay, here. And from the definition, it's actually work over area. Anyone knows the definition of work? This is the definition of work. Force over time. That force over time, no. Force times. If you apply a force on some object and if it moves, only that time the work will happen, right? So basically force times distance, exactly. So that's what I will write down. Force times distance here. And area is what? Length times width or height or anything like another length, right? Now I will modify this one a little bit. I will write down force times length because distance is one type of length, right? And for area, I will write down length times length. So now I can cancel length. Eventually I will have force times length. And that is the definition you will see in your book, that surface tension is the force per unit length needed to separate the molecules on the surface. So basically it's the same definition. We started from work or energy and then we end up with force needed to separate the molecules on the surface per unit length. Okay. What will be the units in SI unit? What will be that? Meters per meter. And for FPS unit? Pounds per foot. Yes, perfect. Yes, so those are the surface tension unit. We got that. And obviously we are studying this because we are concerned about the surface tension. We need to know the surface tension for different purposes. One of the purpose is, I think you are not enrolled in the soil mechanics this semester, right? Because we didn't offer that course. So when you will start the soil mechanics, maybe you already know for each soil particle, obviously there are pores, right? Number of pores and water flows through that pores. So for that purpose, since those pores are very small, the surface tension is very, very important. You will see that when you start the soil mechanics. Some other uses can be like tablet coating, drug solubility and stability. And for cleaning purpose, for painting purpose, those are very, very important, like spray, making the spray from the nozzle. So surface tension is very important for those purpose. We are not going into that much details. So, but just to let you know, but one most important example is in soil mechanics class. Okay. Now, from your appendix A, can you open your appendix A? And you can see for different type of fluid, we can have different surface tension. From this list, which one has the highest surface tension? Mercury, yes. Have you ever played with mercury in your childhood? So this is the first time I found someone.
Well, I mean,
What we did whenever any thermometer was broken, we used to collect the mercury from that, and we used to keep that in the freezer just to check whether it gets frozen or not. It never got frozen because the freezing point of mercury is negative 40 degrees centigrade. Obviously, we can't have that. But it was fun. Don't do that. It's not safe, but it was fun. Okay. So because of the surface tension, as I said, one of the example is the liquid drops. It will be a circular shape because of the surface tension. Now, in your copy, I gave all the details about different type of forces. I will just write down few things here. This is the pressure you apply when you will use that bubble, like when you blow, or that is the pressure you apply, okay? This sigma is the what? Surface tension, right? What about this R? This R is the radius of the what? Bubble or drop, right? And this P at PATM, what is that? PATM? Atmospheric pressure, yes. So if we use gauge pressure, this will be 0. If we use absolute scale, it should be 101.3 kilopascal. Now, I want all of you to blow the bubble you have with 2 different speeds, slowly and quickly, and tell me in which way you get larger diameter. Do that. And you will tell me, do that slowly. For some reason, the slow one is not working here, I think because of the consistency, like the mixture ratios here, but still you will be able to see something. If you do that very quickly, you are seeing the small bubbles, right? And if you try to do that slowly, maybe you will get. Do you mind if I take a picture of you? Okay, I'll bring my cell phone. I'm not publishing it.
See that? See that? Sick. Got a whole bunch of tiny ones.
Now tell me, if you blow slowly, the diameter is or radius is a little bit larger than when you flow very fast, right? That's because you can explain that just by using that equation. If you look at the equation, the pressure and the radius, they are just opposite to each other, right? Now you should get back to the class. Fun part is done.
You don't eat bubble.
Don't eat that. It's the soap water. It's not good. Okay, fun part is done. Now get back to the class. So that means when you apply more force or more pressure, the bubble size will be small, and you can see that from this equation. That's the equation it's telling you. P and R, just the opposite relation. Anyways, I just wanted you to show that we are not doing too much things using that. So another thing can happen because of these adhesion and cohesion. You may have seen these type of things if you pour water in a glass. If you look that closely, you can see this shape. And have you seen this shape anywhere or anything? This type of shape? Maybe concrete or mercury. If you put that in a glass, it will be something like that.
Water on top of it.
That's true. Yes. That's because the shape, this shape actually depends on the relative magnitude of adhesion and cohesion. So cohesion means they are so content with each other, they don't need anyone else. So they will make all the bonding with each other. And for this case, cohesion will be greater than the adhesion. And that's why like they are not interested to make bond with the other particles. But here they are more friendly. So what they are doing here, cohesion is smaller than the adhesion. That's why they are making more stronger bonding with the glass or the container here. Okay. And this tendency is called the capillarity. And for the weighting liquid, that is the condition. For the non-weighting liquid, that is the condition. You have some blank spaces on your copy. You can write down there. I will just write down the example here. This is the water. And this can be mercury, or as you say, concrete, or as the water on top of the penny, it will be this one. Okay. And you can see here is the thing. This is again the mercury. This is the water. Okay. And the last thing, you can actually calculate this drop down or rise, which is called the capillary rise. Here from your textbook, that is the equation, okay? But eventually you take the FE exam, and in your FE manual, they use the same equation with little bit different notation. So in your FE manual, what they did, there is FE manual uploaded on Canvas under this course resource. If you want, you can go through that. So the equation they use is 2 pi cos beta instead of theta, is beta. And can you tell me rho g means what? Like, is there any other parameter I can use instead of rho g? Rho is the density. If you multiply rho with g, I can write down something else. What is that? Specific weight. Yes. So the gamma, right? So instead of rho g, they use gamma and r. So that's what is exactly same thing. Just they use theta instead beta instead of theta. Okay. And due to this capillarities, if you use very thin glass tube, you will have very you will have some difficulties to get the reading because of that capillary rise. It will be like so prominent. That's why it's recommended whenever you do some testing with glass tube, make sure you are using a diameter of 10 millimeter or better glass. Okay. Okay. So in my previous class, I showed something else. We have 4 minutes. I can show you that. Are you seeing that pin is floating on the water? What is the reason? Surface tension. Yeah, eventually it shouldn't float on the water, but it is floating only because of the surface tension. We have 4 minutes. I can try to do that again. Do you want me to try that again?
Yeah.
I have 50-50 success rate. One time I was able to do that. One time I wasn't able to do that, but I will try that. Okay, while I'm doing that, tell me, do you have any question about the surface tension or viscosity or anything related to fluid properties? Do you have any question? I can answer anything. Okay, so what I will try to do, if I just put that here, obviously the density of that pin is greater than water. It will not float on the water, right? But if I try to do this way, I'm using a paper and slowly I will try to remove the paper. Wish me luck so that I can do that. For last section, I had to do that twice. First time it was not successful. So I will try to do that. We have only 4 minutes. Okay. Please. Nope, I was not able to do that. Nope. I can try again. Okay, so next class we will start something new, which is called fluid statics. That is not part of your test 1, but we'll start that because I don't want to give you test on Monday. So Captain Rister told me when I came here first that Monday is the worst day to give you any test, which should be the opposite, right? You get 2 days off, so you should study, but it's just the opposite.
No, it's awesome.
I don't think I'll be able to do that this time also. I did that.
Yes.
You're proud of me, right?
Yes.
I know that.
Well, that's what I see.
Okay, so we are done for today's lecture. Thank you for your time. I will see you on Wednesday. If you have any question about anything, stop by or email me. I'll be happy to answer. Okay, and written the bubble there. Did you have fun with the bubble? Good. You too. Bye.